Before we start the implementation in the editor, I want to show you certain commands in the IPython console so that it becomes easier for you to understand these commands when I write there in the editor. I basically want to show you some intermediate results so it will be easier for you to understand. So let me ask you, what is our aim? Our aim is to have a grid. Then we have to put people on the cells of this grid. Then we have to identify the nodes, which are the people which are unsatisfied, and then we have to move these unsatisfied people to different locations. That is what is the crux. Now, what is the first step? The first step is we want the grid, right? So how do we get the grid? Is there any network X function that can help us to get the grid? So apparently we have this function grid 2D graph, which we can make use of, although not to suit our complete purpose, but we can make changes into that, and then basically we can manipulate that. So let's get started. I'll start my IPython console and let's import. Okay, so let's create a 10 cross 10 grid. So I'll take n to be 10, and then I'll use the function. So I'll write nx dot grid 2D graph. Okay, and we want it to be n cross n, that is the 10 cross 10 in this case. Okay, so this is the function that we will use. Let me show how it looks like. So I need to show that. So I need to import matplotlib.pyplot as plt. So I'll write nx.draw g and plt.show. Okay, so this is how it looks like. Obviously it's not looking so good. It's not even looking like a grid of but it is a grid, although it's not looking like the way we want to show it. So we might need to make some changes into it. Let's see what kind of changes we can make here. I am going to close it. The graph is not looking so nice because the nodes are not displayed in the form of a grid. Apparently we don't have any grid layout in network X, so we might need to manually assign the positions to the nodes. Now, how can we do that? Before I tell you that, let me show you the nodes of this graph. So I'll write g dot nodes. Now there's something different here. In the other kinds of graphs, we get either some number or some user-defined string as the label of the nodes. But here, see, I wrote g dot nodes, and what I'm getting is I'm getting a tuple for every node, and the tuple consists of two values, which is basically the row number and the column number of that node. So basically it is like a grid, but it's just that it's not looking like a grid. So we might need to display it accordingly. We might need to assign appropriate positioning to every node. So I'll show you how we can do that. Please note that we are getting both x and y positions, which are relative positions of these nodes with respect to each other. So what we can do is I'll write n comma n for n in g dot nodes, or since we have used n capital N already, maybe I should use small n. Okay, so what I'll write is I'll convert this into a dictionary, and I will assign that dictionary to a variable, say pos. Okay, let me explain you what I have done. So these are g dot nodes, as you can see. Please note the pattern of the nodes that we're getting here. So this 8 comma 8, for example, will be 1n. So what I'm doing here for n in g dot nodes, that is for all these tuples, I'm writing n comma n. So I'm creating a tuple where there are two n's, n comma n. So it will be like 8 8 comma 8 8. Okay, what I'm doing is for a node I'm fixing its position, which is the same as its label. right? So and after that I'm converting that into dictionary, because that's how we pass. The parameter that we pass should be in the form of dictionary. So this dict function, this is the function in Python. What it does is it converts a tuple into a dictionary, where the first value of the tuple will be the key and the second value of the tuple will be the value of the dictionary. So this pos, this is the positioning that we have fixed, and we can assign these positions to the nodes. Now how we can do that is we call this function nx.drawg. We can pass this positioning here, and then we can write plt.show. All right, this looks beautiful now, isn't it? Right, so as you can see, we are getting the grid. Another thing that we have to note here is that the labels are not looking so nice. One thing that you should note here is that 0 0 is here and in the bottom left corner, and it goes like this: 0 0 0 1 0 2 0 3, and then comes back from 1 0 1 1 and so on. So this is the default sequencing of the nodes that this function provides, that we used grid 2D graph. If you want, you can change this label in such a way that 0 0 appears here, but I don't think we need that, so we'll let it be like this. But one thing that we would want to do is that we would want to change the label. Basically we have 10 cross 10, that is 100 nodes here, and it'll be nice if we assign them labels like 0 to 0 1 2 3 up to 99. So that is one thing that we would like to do here. Now let me show you how we can do that. Again, we will assign a different label to every node. Now the name of the node itself carries the row and column number. That is what we will be using in order to assign the label. So the 0 0 should be having a label 0, 0 1 should be having a label 1, and so on, 0 1 2 3 4 up to 10, no, 0 up to 9, and then 10 should be here, then 11, and so on. So this is how we have to assign the labels. Now how can we do that? If you know a little math, you should be able to understand what I'm doing. So what I'll do is I comma j. To I comma j, what I'm assigning is I into 10 plus j. This is what I'm assigning to the first node and to the ijth node. This I will do for every node, so I'll write for ij in g dot nodes, and again I'll convert this into a dictionary. So I'll use the same function, and let me call this dictionary labels. All right, this should work. So what I'm doing here is that to every node which is ij, like here, like 4 3, I'm assigning a label which is I into 10 plus j. In the case of 4 comma 3, it will be 43. So that label I'm assigning to every node, and that information I'm keeping in the form of a dictionary in this dictionary called labels, which I'm going to use. So let me show you how we can do that. So we used nx.draw previously, which displays some labels by default, which is the labels that I showed you just now. We don't want those labels to be displayed. So what I'll write is with labels is equal to false, right? So the labels that it was showing will not be visible. You can check that as well if you, I can quickly show you. So there are no labels displayed here. Okay, now we want to display our own labels. For that we have a function nx.draw network x labels. Now again we have to pass the graph, we have to pass the positioning, and then we have to pass the labels dictionary. Labels dictionary. Okay, this is how we write labels is equal to labels. Okay, this should work. Now the new labels have been assigned. Let us display them. Oh yeah, this looks nice now. So we have the labels from 0 1 to 3 up to 99. So it'll be nice to refer to them when we do the later manipulations. Okay, now one thing that is important to note here is that I told in the explanation of Schelling model that every node which is an internal node that is not on the boundary should have 8 neighbors, right? Now here if you look at this node number 45, it has 35, 46, 55, 44. It has only four neighbors. It is not neighbors with the diagonal nodes, as you can see. So this is the kind of grid that the function provides us by default, but this is not serving our purpose. Our purpose is that this 45 should be connected to 56 as well, as in all these four nodes: 36, 34, 54, and 56. Now how do we do that? So we would have to add the edges manually, which are not already present here. Now how can we do that? I want to show you the previous representation of the graph, because that will help us understand um how we can add the edges. So what I'm going to do is I'm not going to use this command. Okay, nx dot draw, the usual function that we were using, and this position we were using. I would like to display this only. Okay, I'm showing you the previous version of the graph for a reason, because I want to show you how we can add the edges, the diagonal edges. Now if you look at this 1 1 node, we have to connect it to 2 2. This 2 2 has to be connected to 3 3. And if you look at some other node, this 2 6 has to be connected to 3 7. 4 8, 3 7 has to be connected to 4 8. So if you observe carefully, the node ij has to be connected to I plus 1 j plus 1. If you look at 6 7, it has to be connected to 7 8, which is again I plus 1 j plus 1. Okay, so we will take all the nodes ij and we will connect them to the nodes I plus 1 j plus 1. That should be half of the work done. So let's see. One thing that we have to note here again is that when we are doing I plus 1 j plus 1, it should never cross the 9, right? We cannot connect 9 9 to 10 10. So that limit we have to take care of. So that we will take care of that thing. Okay, so I'll write for u comma v, let's say, for uv in g dot nodes. What do we want to do? uv has to be connected to u plus 1 v plus 1, but again we have to take care that u plus 1 and v plus 1 doesn't exceed n minus 1. So I'll write if u plus 1 is less than equal to n minus 1, and the same to be done for v. So I will write v plus 1 is less than equal to n minus 1, then only we'll do this. Otherwise we will not add that edge. So I'll write g dot add edge. Which edge? uv edge to u plus 1 comma v plus 1 edge. Okay, this should work. Let's see. Okay, let me show you the graph at this stage. So I'll write nx dot draw and then I'll write pd dot show. Yeah, so we have we have half of the diagonal edges incorporated already. The other direction of the diagonal edges are still yet to be added. For example, we have to connect this 3 9 to 4 8, 4 8 to 5 7. So that has to be done. Now if you observe carefully, 4 6 has to be connected to 5 5, which means uv has to be connected to u plus 1 v minus 1. Yeah, that holds true for every node. Now again, one thing that we have to take care of here is that while doing v minus 1, it should not become less than 0. So that part we will take care of. Let's see how we can do that. I'm going to make changes here itself, or yeah. So what I'll do is I'll go back here, and if u plus 1, so uv has to be connected to u plus 1 v minus 1. So u plus 1 should be this, and v minus 1 should be less than equal to, no, should be greater than equal to 0. Okay, it should not be less than equal to. So this we have to check, and if this is true, then we will add an edge from uv to u plus 1 v minus 1. Okay, this should work. I'm a little doubtful about the indentation, but let me see if it works fine. Yeah, so here you see all the edges have been incorporated, all the diagonal edges are there. Now the grid seems complete. Let me just show you the labels, the updated labels that we recently showed. Which command did we use? Yeah, we use this, and then we used which one? This one. Okay, yeah, let us see. Okay, this looks nice. So we have the grid, we have the diagonal edges, we have the nodes. Now we have set the playground for for playing with these nodes, where we will put the people of different types. There'll be some people of type 0, there'll be some people of type 1, there'll be some nodes which will be empty. We will not put any people there. So that is how we're going to start. In the next video, I will be using all these commands that I've shown you already in the IPython console. So I will use them in the editor, and then we will get started with manipulating the nodes.